He has been running a publication called Decipher with Zarab, aiming to help Web3 developers become a better smart contract developers. So over to you, Zarab.
Sure. Thanks, Tushar. Can you guys confirm if you can hear me okay?
Yeah, we can hear you.
All right, perfect. Cool. So let's get started. Before I share the screen, maybe I can quickly introduce myself. Tushar already mentioned a lot of it, but I am Zaryab. I basically work at Push Protocol as the blockchain lead, and most of the team that I have managed is basically around smart contract developers. In Web3, I basically entered as a smart contract dev, but I also worked in the auditing phase for 1 or 2 years. As of now, most of my job and most of my life revolves around building smart contracts or auditing smart contracts or writing about smart contracts. So in a nutshell, it's just everything around smart contracts. Uh, what we're gonna do today is uh, I'm assuming most of you have some knowledge about what Solidity is about and what smart contracts behave like. So we're not really going to explore the basics of what smart contracts are. I'm assuming most of you are devs. So I what I will like to introduce you to is basically what it means to develop smart contracts in the real world. When you are supposed to deploy it on production in mainnet, when you're actually using real money that is to be stored in the smart contract. For instance, the contracts that I have built so far, as of now, it stores around 2 million or 2 million plus dollars, right? So the point is, it's a big deal when you write code that stores money. And if it's a big deal, if it's a responsibility, then you have to approach this craft accordingly. So my whole idea for this presentation is to just give you a glimpse of different sections of smart contract development and what it looks like to build a production level contract. Secondly, what it looks like to optimize those contract. And maybe you have heard of gas optimization, but I'm going to talk much more than that. I'm going to talk about how to optimize the size of the contract as well, not just with gas. And then maybe lastly, we can touch a bit on what is security looks like in smart contract. So with that said, I'm going to share my screen and let me know if you guys can see the screen properly. Is the screen visible?
Yes, it is.
Perfect. And by the way, this is not going to be like a typical PPT session. The PPT is already there, and the only reason it's there is just to give us some reference points. But what the way I'm going to take it forward is I will walk through things. I'll also jump into Remix and show you some code. Maybe I'll jump into the actual contract that I have written in Push Protocol. Maybe I'll jump into some production level contracts of Uniswap, Sublime, or all the other repositories that I admire, and I'll keep dropping those links in the Google Meet chat. So I think that's more valuable than just going through PPTs. So that's what I'm going to do. Maybe at the end we can have a short Q&A session as well, where you can ask questions about anything that you want around smart contracts. So that's going to be the format. Be attentive and maybe just highlight the things that you want to ask at last, and just follow the links that I will share in the chat box. All right, so that's basically the intro, but let's plan the journey ahead. So for the next 40 minutes or 1 hour, I'm basically going to go over three important parts. Uh, the first one is the basics of building a Solidity code base. And this is not about building a setter and getter function Solidity code base. It's about what it takes and what exactly should you keep in mind when you are building a code that is to be deployed on mainnet, on any mainnet, Ethereum or Solana or whatever. Uh, Considering that it's a smart contract, you know that it's immutable. You know that you cannot change things up once you mess something up, once it's deployed on prod. So it becomes incredibly important for you to understand that when you approach writing a smart contract is not similar to writing any web2 application where you can anytime go and change things in production as well. And it's a huge step to change anything. I mean, maybe you guys know about upgradable contracts as well, but in case you have been seeing the news in web3, you know that upgradable contracts are not secure as well, and there is a lot of things that can go wrong even in upgradable contracts. So the first point that I'll go through is very important tips. Some of them maybe you already know about, some of them you might hear for the first time, but that's basically it. Like, how do you design a contract professionally? Second will be mental models that I have learned so far around optimizing gas plus optimizing the size of the contract. And I'll tell you why the size optimization is important as well. And the last one is security. So as a developer, or maybe in case some of you are in security, I'll share some tips that might help in terms of auditing or developing both. So a lot to cover, but let's get started and let's see how far we go. So stage one is basically designing a smart contract and how does it look like, right? So even before going on step one, just to highlight why it's important, step zero is to be very, very specific. And I'm talking about building smart contracts which you will deploy on mainnet, which basically means it's important. So step zero is not even writing Solidity. It doesn't matter what the code is going to be. Writing the code is very easy. Designing the logic or the behavior of how the code will work, that's the most important part, right? So when you are building a smart contract, let's say from scratch. So for example, when I joined this company, I was the one who started writing the contract from very scratch, right? So there was nothing there and I started it. But maybe when you join a company, there might already be some code and you are supposed to write one specific function or feature of that code. Even then, it's very important for you to be super specific of what exactly you want to write. Uh, and the reason for that is unless you are, uh, you will end up going through a rabbit hole which might lead to nowhere. So Solidity in itself is a very simple language. In case you're coming from JavaScript, you might have seen the similarities already. It's super simple, right? So if you know JavaScript, you can easily catch on to Solidity. It's very simple. But the hardest part is writing it securely and optimizing it very effectively. So it's not the writing part. It's optimization part and security part. So being specific and the step zero means that even before you build a specific function or the entire contract, just have SRS. SRS basically means software requirement documentation sort of thing, which actually tells you what exactly is required, what exactly are you building. Maybe you are building a DeFi protocol, maybe you are building uh, any sort of governance system that you need to design. And in all of those things, you need to be very sure about what the next step is going to be. If you're building a governance proposal, for instance, you need a governance contract, for instance, you need to know how many proposals do you want to execute in one transaction, what should be the delay period, how does the time lock work, who has the access for creating proposals, is it based on the number of tokens that the people have, or is it based on just access control rules? So even before writing Solidity, as you can already see, there are tons of questions that you have to answer before getting to the code. So I recommend don't even bother about the code. The code is simple. Decisions are hard. So spend some time writing a doc and then move to code, right? So let's assume you have already done that. You already have a very specific idea of what you want to build. Then we come to the Solidity part. So maybe now we can understand what a code looks like. So I have a Central DAO specific folder here that I created to save some time. Uh, there's this standard code, which basically how Solidity code should look like. So it's going to be very simple. All right. So the next topic is, and again, we are still talking about how to write smart contracts professionally, right? So the header of the contract that you might have already seen, which is this, the Pragma version, the license, and the imports, right? This part is important as well, and often people don't know what it means to have it fixed or not fixed, or let's say logged or unlocked versions. So in case you're building, and the difference is very simple, for the uh, statement, the pragma statement, if you are building a contract that you know is for your own purpose, right? For example, the contract that I write for a particular company, I know that it's just a contract that will be used by a specific user set and not by other people in the Web3. I can lock it to a specific version. So I can make that pragma like this. So it basically means 0.8.20 is the version that is locked for this contract, and that should be fine. But if I'm building a library, which I would essentially want to open source, and maybe that library will be used by different projects with different versions, right? Then it makes sense for me to have it as unlocked, right? So that any version, any contract that might have a different version will still be compatible by using that library. So that's the first part. That's the pragma part. Now, how do you decide which version you use? So a basic thumb rule is that do not use a lot older versions in your contracts. Um, but do not use the very latest versions as well. Usually latest versions are safe. So the thumb rule is, before deciding what to use, usually prefer to use the latest version. So what version you use. Using extremely older version will be a bit tricky because Solidity is at its very nascent stages, right? So with every version, there will be something that is breaking. There will be something that might not work in the latest version. So you always have to keep that in mind. Secondly, imports. So it's pretty simple. Whatever library you want to import, you can. Uh, but then there is a specific structure for that too. And usually this is not the way you should import. And there is something called name imports. So if you basically want to import a specific library from a set of libraries, then this is what you do, right? So this is called name imports. This basically means you are being exactly selective of what you want to import from this particular library, right? And, or what contract you want to import from a particular module of OpenZeppelin. And this makes the code more readable. Again, we are talking about being professional. So you have to do some sort of work to make your code readable and maintainable, right? That's just the basics. So now let's go into what does a contract look like, and what is the order of layout in terms of the Solidity docs. And by the way, whatever I'm saying, you can always go and check in the official Solidity documentation, and there should be a order of layout as well. So, for instance, this one, right? Uh, make sure you check this out when you have some time, because it's important to keep the docs in mind. So I'll drop it here. So in general, this is what uh, order of a contract looks like. It's you declare the types, which is whatever struct states, or let's say you have your own custom defined data types. You write those things first. Then you define the state of those contracts. When defining states, it's also important for you to define what their visibility is. Is it publicly visible? Is it not? Is it just meant for internal use of a contract? Then you mark it as internal, uh, or is it supposed to be private? Um, then you have the events that you want to define in the contract. Then you have errors. And I'm assuming all of you know what custom errors are. And in case you are still using require or some older format of error handling, I would again recommend to shift to custom errors. And maybe there is one slide that explains why to use custom errors. Then you set up your modifiers and you define your modifiers, and then the functions comes in, right? Um, when we talk about state variables, the way you name them is very important. Um, quite often than not, it's very hard for us. Let's say I've been in professions where I have reviewed code and also written code. So when you review a particular code and the naming pattern is not consistent, it's very hard to review, and those hard review parts might leak some bugs that I cannot might not be able to find, right? So be very consistent with what you name. Whatever you name should be readable enough, should make sense, instead of naming something like A, B, or C. uh, then comes use immutable and constant wherever necessary. So these are keywords provided by Solidity, right? And if you know that a state variable in your contract is never supposed to change or updated in the entire life cycle of the contract, just mark them as a constant or immutable variable. Uh, Third point is private isn't private, which is an important point. In case you already know what security in Solidity looks like, you might know this, that even though you write something as private. Let's say I have written the name as private, which basically means this is not visible directly. If I deploy this contract on Etherscan, you might not be able to see it, what the name of the contract, name of this token is. But private in smart contracts doesn't mean that it hides that data completely. So there are still ways for me to just check the slot of which slot this variable is in, and then fetch the value of that variable. The point that I'm trying to make is never store anything private or sensitive within the contract. And how exactly does it work is, let's say, a homework for you guys. Go figure out how exactly can you fetch the value of a particular state variable, even though it's private. And I'm telling you it's possible, right? So TLDR never store any sensitive information, let's say a password or an important byte hash. on the contract, thinking that, okay, I have marked it as private, so no one will be able to see it. It's very visible. It's just a game of bytecodes, and I can still fetch it. So keep that in mind. Whenever you use Solidity, Solidity has grown up to be a really beautiful language now. So it provides a lot of uh, utility names. For example, I can just show you here. So for instance, if you're using times, right? If you want to define, let's say a proposal should not be executed for 7 days, and to include those 7 days, you are multiplying it into 60, into 60, whatever. Instead of doing that, it's very easier for you to just use this keywords, which is days, hours, or weeks, and you get the definition here, right? Uh, Quite often I see contracts which basically write like this, which is, let's say it's going to be a 100 ether, so they will write 100, and then they will write 18 zeros, which is this, right? And this is very, very not recommended. It's not readable. Instead of that, you can just do this. So Solidity still provides a lot of utility keywords that you can use. So make sure when you write a contract, first of all, there are two things. So when you write a contract, it's not just for you; it's also for everyone in the on the Web3 world to see. Secondly, your contract is supposed to be reviewed. So make sure the person who reviews it doesn't have a hard time, because if a lot of his time goes into deciphering what you have written, then the bugs that might be there in your contract might be it might be hard to find them, right? So try to make it as readable as possible. And that's about the state variables. Now, if we go to functions, uh, this is what the order of functions looks like. So you initially start with a constructor, then there is a receive, a fallback if they exist. Uh, Usually it's recommended to mark all the external functions first, public, and then internal, and then private. And within each of these groups, if you have a pure or view functions, I'm assuming you already know that in view functions, you cannot update the states of the contract. So those functions should be grouped together and at the very least, right? So the way the function keywords work and the right structure is visibility, mutability, virtual override, and your custom modifier. What that means is here. So let's say we are talking about this function and we are defining one function, right? So as per the standard Solidity, you name the function, name of the function, you pass some sort of um, parameter, and then the order that we should follow usually is visibility, mutability, virtual override, which means this. By visibility, what do I mean? Uh, by visibility, I mean that this function that I've just defined here, let's say this is ABC, who exactly should be able to access this function? Is this function supposed to be accessed by everyone in Web3? Then it's external, right? Or is this function supposed to be uh, accessed by the contract as well as externally? So it's supposed to be internal then, or it's supposed to be internal or private. Now, maybe anyone of you can unmute your mic and say, if we already have internal, why do we need private as a visibility specifier? Feel free to unmute your mic. Yes, there is no rule for that. Hey, Deepak.
Yeah, private adds more security since internal, while using internal, it can be also called from the derived contracts, but in private, it can be called only inside the contract.
Very close. Yes. So if I use internal, I can call it from the contract itself, right? So if this is the contract, which is my token, if I name this function as internal, that basically means I can call this function from the contract itself, right? And if I write it private, then I cannot.
We cannot call it from the derived contracts, which is deriving this contract.
Yes, which is inheriting from this contract, right? So the reason for having this specifier is, so if I mark it as internal, that basically means this function cannot be called from anywhere outside. But it can still be called from other contracts which might inherit this contract. So maybe I have a different contract called XYZ, and that inherits this contract, and that XYZ will have access to this. But private is the most strict restriction, because once you have added private, that basically means even the contracts that is inheriting from this will not be able to access this function. So those are the reasons we have visibility specifiers, and it's really important because they add a layer of security on top of every function that you want. So first was and thank you, Deepak, very nice answer. First was visibility. Second was mutability, and that means what? That basically means whether or not this function allows mutating the state of the contract. Uh, if it doesn't allow, then it basically will be view, which basically means you can only access things from here. You can only read, but you cannot write to any state if you have view. Else we can just leave it like that. So that comes next. Then comes virtual override, right? Anyone who would like to explain what this means? What is virtual? What is override?
Virtual can be used when the contract is abstract.
Mm-hmm.
So those kind of times we can use a virtual keyword. So for
But why?
it doesn't
If a
have
contract is
any
abstract.
implementation of the function, so we can add our customized body.
Right. Perfect. So if a function has virtual, that basically means if I am inheriting that contract, or if I'm using that contract, I should be capable of overriding that particular function on my own with my own logic, right? Else I won't be able to. And if a function is having override, that basically means that uh, this implies that I have overridden some of the logic of my own, right? And the last part is having custom modifiers. So let's say you have your own modifier set up, which is only owner, which basically means you're only allowing the owner state address to access this function. So you have that. So the layout in a function is you name it, you pass the visibility first, then the mutability, then either you want to have it virtual or not, or you are overriding or not. Based on that, you write it here, and then you write your own modifier, and that again depends if you have those modifiers or not. But this is the right layout of a function. All right. And then the last point basically is that naming those functions properly is very important, because people assume the behavior of function based on their names. And like I said, when you write smart contracts, it's not a hidden code. Everyone has access to it. So if you have written the function name very inadequately, that basically means people might wrongly assume what that function does, and they might call it, and there might be some loss of funds. So make sure that you name the functions exactly, precisely what they do. So yeah, this is just what I explained. Is just a structure of what functions look like, right? Now it comes to code readability and NatSpec annotations. So in Solidity, there is something called NatSpec annotations, where you are able to provide documentation within the code of what each and every function does, and I'll explain why that matters. So before that, let me just go to, let's say, the push protocol is smart contracts, right? So this is the branch where we have recently pushed some changes. So if I go to contract, and if I go to, let's say, core, first of all, you see that all the imports are named imports. And whenever you see a function, for instance, if I go here, so let's say this is the function that allows you to create channel, right? Everything about that function is documented in the NetSpec, and NetSpec is basically a standard that Solidity provides, so that you can write within the code what each of these function do, right? So notice is what this function does. Dev is any specific pointer that I would like to highlight for the devs who are exploring this contract, for example, for exploring this function. For example, this contract, this function will only allow users to create one channel for a specific address. That's a condition that I would like to highlight for the developers. It validates and transfers the amount of push token from channel creator to the contract. So that's the second point that I want to highlight. Then comes the parameters. What all parameters does this function takes in. Once you have NatSpec annotated code like this, it makes it super interesting and super helpful and readable. And anyone who reads it understands what this function does. But that's just one benefit of this. The second benefit is if you go to Etherscan and you look at the same contract, for example, let's say create channel. So this is the function, right? Etherscan captures those statements that you write in your Solidity NatSpec annotations, and it provides it here. So you understand how useful it is. Now, anyone who is interacting with the contract and who is coming to Etherscan to directly interact with it, they know exactly what it does, which basically means you don't really have to understand Solidity. If you are a normal user, you can still understand what this function does, and you can interact with it based on that, right? So it's your responsibility as a user to make your contract extremely readable, so that Etherscan or so that anyone who is exploring your contracts will be able to understand what the code is doing, right? Uh, Second part is that I just explained, naming of function variable matters. So make sure you do that. Third point is code consistency is beautiful. So that should be valued. If you are naming, let's say, addresses in your contract in uppercase, make sure you are doing that every time, right? If you are using underscore to bifurcate between different names, make sure you do that and continue doing that in the throughout the code. If you are using camel case, make sure you do that consistently. When you break the consistency, it becomes again hard to read. Fourth point is grouping of function and states in a logical order. If you have, let's say, 5 get functions which only allow you to read a particular state, and then you have 5 setter functions which allow you to modify a particular state, and you mix and match everything, and you provide just a mixture of all those functions in the contract, it makes it very hard to read. Again, hard to understand. And understand this, the reason it's important for you not to mix and match things and to maintain the readability is because smart contracts are able to interact with each other as well. So the contract that you write, chances are, if it's very well written and if it provides value, someone else, some other Solidity developer can also interact with your contract on chain. And if you are making their life harder as a developer, chances are your contract will not be used because it's just not readable. So it's very important to maintain the consistency for that as well. Fifth point is important, which is avoid deep nesting or bloating of functions. Usually if you are coming from a different background, which is, let's say, Python, JavaScript, whatever, writing good clean code is always valued. But even if you don't do it in other languages, you are not punished. But in a smart contract world, you are punished, and technically you are also punishing the user, because it will become heavy for their wallet to interact with your function, because your function is just too big, or it has a lot of if statements, or it has a lot of heavy loops that it runs, right? And when someone interacts with that function, they are paying a lot of gas. And so it's your responsibility as a developer to write functions that are very, very clean, very, very easy to use, and very cheap to use as well. So if you avoid deep nesting or a lot of if conditions, or find better ways to write contracts or functions that use less gas, that's always advisable. Modular functions basically mean you break them down into smaller chunks so that you can maintain the readability, also reusability. So you can reuse those functions again and again. So these are a couple of pointers to keep in mind when you are writing a smart contract, right? Now, one way to understand, and this is a cool example, for example. So one way to understand how to write good code is to always look into other protocols. Let's say I have recently been exploring the Sublime code, right? And the way they write Solidity is very interesting, and it's very helpful for you as a Solidity developer to learn as well. So if you go to their contract and they use Foundry, and if you look at their code, it's very, very clean. It's super awesome to read, and you just understand things at the moment because they have NatSpec annotations. Their function naming is very right. They have test cases, which is following the BTT technique. I'm not sure if you have known about this, but there is a technique called BTT. Again, I'm going to drop this in the chat box so that you can read about it later. And it's a way for you to test smart contracts thoroughly. So if you, the last suggestion is if you explore other contracts, Sublime or let's say Uniswap, you will still get a lot of good value because you will understand how contracts are written in the real world. And trust me, that's what makes you better, because like I mentioned, anyone can learn Solidity and anyone can write Solidity. So that's not the trick. That's not what makes you in the top 1%. What makes you the top 1% is if you can really write Solidity code that is optimized and well secured. So that's what makes you unique as a developer. Now comes an interesting topic, which is, all right, I can write clean code. I can maybe not bloat up functions, and maybe I can also name functions very effectively, and I can write very, very clean code. But what if, let's say, I have a smart contract that is upgradable, and what if with every new version that comes in, my code gets getting larger and bigger, and it gets very hard for me to organize the code. And trust me, that's going to happen if you work in a company that has upgradable contracts. For example, Push, the company that I work for, they have upgradable contracts. So which basically means with every version, I'm introducing new functions. And eventually there will be a time when the contract size increases. And I'm come to the size part a bit later, but right now I'm talking about organizing a large code base. So there are a couple of tricks to keep in mind when you're doing that. Usually in Solidity, we are used to this structure, which is, hey, why not just write everything in the same contract, write the states, write the mapping, write the events, everything in the same contract. But this works in this contract because there are very small number of state variables or very, very few number of events. But if you had, let's say, 15, 20 different states, right? And you had a bunch of different events and you had a bunch of different mappings, that basically means you would take 100 or 150 lines in this contract just to mention your states. And that will be a bad idea to organize the code or to reduce the size of the code. So for instance, if you look at the code that we write, there are different files for um, writing states of a particular contract, right? So if you look at this file, this only includes the state variables. It has no functions, it has no events. It is solely created to store all the states of that particular contract that we will use. And storage v2. And what we do eventually is we just import those files in this contract. So what we're able to do is we are able to make a slightly better system for maintaining this code base in the longer run, because now we know that whenever you want to write a state, we don't write it here. We just simply go and write it in the storage file, which the purpose of which is just to store the state variables. So one suggestion, the first trick is uh, bifurcate. So like divide those files into different sections and write the states in a completely different file so that it's easy to manage in the longer run. Second trick that you can use is that if there is a function that uses a lot of different parameters, let's say more than 5 or more than 6 parameters, it's always recommended to use a struct in that scenario. So I mean, you might know this, that in Solidity you can use a struct to pass as a um, function argument. Let me see if I can provide you some examples on that. Uh, yeah, for instance, see, when you see this function, you are basically seeing that if there is just one parameter and that's a UN256 and that's being passed. So that's completely fine. But when you see this create with deltas, what you see is they're passing a basic struct as a parameter, because I'm pretty sure that this struct has a lot of different elements that they want to pass in this function. And instead of defining all those elements like UN256, address, bytes, or whatever in a function argument, you can just simply uh, wrap them up in a struct and then pass the struct as argument. And that makes the function very small. And it's also optimized way of writing code as well. So that's a second trick that you can use. Third trick you can use is you can leverage libraries to group similar functions together. And libraries has a additional benefit of saving the contract size, which again I'm coming to in a few minutes. And fourth point is, like I said, you need to learn from other projects almost every day. So part of being a smart contract developer is also being a student of Solidity or smart contract development throughout your life. So you have to keep learning every now and then, because first reason is Solidity versions changes rapidly, and with every version there is some sort of breaking change. And it's not just about Solidity. Even let's say popular tools or popular libraries like OpenZeppelin, they keep launching their new versions, and to keep up with that, you have to understand what each and every version is bringing into the space, right? So learning from different projects, which are good ones, is always a good tactic that I use. Now comes the interesting question, and maybe now we're entering into the second stage of the presentation, which is, what if your contract size keeps getting bigger, right? So it's fine that we have a organized file now. So we have good clean code, and we have been able to organize it. We have been able to write different files of states in a different file. We are using libraries and all, but you have upgradable contract, or you have a contract that keeps upgrading in every new version. There are new functions, and your contract is getting bigger, right? Why is that even a problem? Like, we have seen codes that have thousands, 10,000 lines of codes. Why is this a problem? The issue is, and for this, I'll not rely on the PPT. I'll directly go to one of my well-created article series on this one. So let me just go there. And this is the site where you will find the articles that I've written. So maybe some of the references I'll give is from this site itself. So if you go to article series and you go to bytecode size limit. So the problem is that, specifically talking about Ethereum, there is a specific size that you can write the contracts into. And the problem occurs when your contract becomes so big that it exceeds this size. And if you exceed this size and you try to deploy the contract, you will get this error, which is contract code size exceeds 24 kilobytes. And this was a limitation introduced in a specific version of Ethereum, and then you will not be able to deploy the contract. So even if you have written the code properly and you have a lot of nice function, doesn't matter, because your code will not be deployed because you have been exceeding the size, right? You can read the article in detail of why this is a limit. So in a nutshell, it's basically like, to maintain the performance of the network, there is a specific limit to what contracts you can deploy on chain. But that doesn't matter. The fact that there is a limit for smart contract developers, it means that now we have to not only think about optimizing gas, which I think you already have read about, but this is something that no one talks about, which is optimizing the contract size as well. If your contract keeps getting bigger, you need to know what all you can do to shrink the size down to make it lie below the threshold of 24.5 kilobytes. And unless you do that, you will not be able to deploy. So yeah, this is just a meme, which is, you don't have to optimize gas, you also have to optimize contract size sometimes. And here are a list of things that you can do, and I'll dive into some of them, which is really interesting. First obvious trick is to minimize the redundancy of the code. If you see that there are functions in your contract that can be reduced, replaced, or completely removed from the contract, you do that first. You try to optimize as much as you can from your own intended behavior perspective. So if you know that there are getter functions that are not really needed, because let's say there's a mapping and it's public, you know that the mapping can always be used as a getter function itself, right? So you remove any getter functions that read from the mapping. What I mean by that, let's say, is this. So if I have this mapping and let's say it's public, so whenever someone from the in Web3, they pass the key here, they will get the balance of that user, right? You don't really have to write an additional getter function for this, which is get balance, and you pass address of user, and then you again check from the balances mapping to return the value of this user's balance. So, and you return it here. Point is, this is completely useless. You don't need it because it's a public mapping. It's a public state variable, and anyone can get the value from here itself. You don't need to have additional setter function, a getter function. So the first step is to reduce such functions that are not really needed in the contract, so you can reduce the size of the contract, right? Second part is that I just explained, is to use libraries as much as you can. So let's say if you are writing a code which is required to calculate percentage based on the parameters passed. So you pass two parameters, one is value and the second is percentage. And based on that, you find what percentage is X of that value, right? You can do this in a library. You don't really have to put this code necessarily in your own main logic contract. And once you shift this to libraries, what you're essentially doing is you're reducing code in your own contract, which in a way reduce the size of the code in your contract, right? Uh, there is something called a diamond pattern that again it's beyond the scope to explore in this session. But again, like I said, I'll keep throwing links at you so that you know what to read when you're back from the session. So I'm going to drop it here. And this also allows us to reduce contract size significantly. Um, the next trick is to use smaller data types if possible. So you don't really have to use big data types all the time. Uh, the next one is, I'm going to come to this in a detail in a few minutes, but when you use require statements in a contract, in a function, and let's say you use very lengthy messages in that require statements, you might not know this, but the longer your message is require statement, the longer, the more space it uses in the contract, and the size of your contract increases a lot. So reduce those require statement error messages, or even better, switch to custom errors. And that's why I started by saying that you should shift towards the latest best practices of the smart contract, which is custom errors instead of using required. And I'll tell you why custom error is better. So, all right, these are a couple of tricks, right? Now let's get into some of the interesting ones. So let's start with the custom error part. So just look at this. There are two simple examples on your screen. First is a simple contract that uses require statement to handle a particular error scenario. So whenever the caller of this function is not owner, it will revert, right? And the second contract does the exact similar thing, but instead of having a require statement, if just checks with the if revert statement, which basically reverts the custom error. And again, if you have not known about custom errors, if you don't know what it is, please read about it. But I'll just give you a brief idea of what it helps with. So in the second contract, there is a custom error defined here, and there is a revert statement with a simple if message. Uh, and it does the exact same thing. And if you see, both the contracts look exactly similar. They are almost same size and same lines, right? But if you really look deep, when you compile both of these contracts, here is what you get. So the first contract with the require statement has 1556 bytecode characters, and the second one has only 1288 bytecode characters. If you are not aware of what bytecodes are, I'll show you in a minute. Um, but what this essentially means is that when we are using require statement, the size of the contract increases. But if we are simply removing it and using custom errors, the size decreases, right? And the reason for that is, like I just mentioned, if you are using a require statement and you are passing a lengthy message, error message, uh, that gets accumulated in the bytecode size of the contract, right? So the longer your message, the longer the size it will take. But in case of custom errors, we are basically using function selectors to identify them, right? Which basically means that function selectors are 4 bytes only, irrespective of what their actual size is. It's just 4 bytes that we really care about. So it doesn't really matter. And it actually is reducing the size that we are using for handling the errors. So due to this reason, we are able to save space in a contract if we simply remove all required statements and replace them with custom errors. And that will help us shrink our contract size. And it's really important. You should go and try this out. Maybe deploy both of these contracts on Remix and then see the bytecode size. What I mean by bytecode, by the way, in case someone doesn't know. So see, whenever you write a contract, you're writing it in Solidity, which let's say it's basically English language, right? But when you deploy it on chain, what happens is this. It gets converted to something gibberish like this, which you cannot understand. but this is what we call as bytecode, right? Now, there is a article that I have written on this, which basically explains the entire journey of the smart contracts from the time you write it and the time you deploy it on chain. So that is something that will give you a good idea in detail about what bytecodes are. But in a nutshell, you need to understand that when you write Solidity, it's a language that humans can understand. But the moment you compile it and deploy it, the Ethereum EVM machine, which is supposed to understand transactions or execute or instructions of what it needs to do, they understand bytecode, right? So this is a machine readable list of instruction that the EVM understands to execute a particular task. So all those code that we write essentially get converted into this bytecode form, right? And the more the size of this bytecode, the more the size of your contract. So when I say reduce the bytecode size, I basically mean write your code in such a way that this bytecode size that you see, it gets reduced a bit. So right now, what we just discussed, required statement versus custom error. If you use custom error, chances are you will have less of this gibberish, less of this bytecode, which basically means you have been able to reduce the size of your contract, and which is helpful. If you reduce the size, it also means that when you deploy the contract, you will pay less gas than when you have a very big length of bytecode. So that was one trick that we just explored, right? Second is a very interesting one, which is about modifiers and functions. So again, if your contract is getting very bigger, and this is something I also did in my contract uh, recently. So one additional trick that you can use is removing modifiers with simple private functions. So what do I mean by that? Let's say consider this smart contract, right? Um, so what this is doing is basically is a simple smart contract that has an owner variable, and it has a modifier which only checks that only owner should be able to call, right? Or the owner is not address 0, whatever. And all the functions that we have in this contract, they are using only owner, only owner, only owner modifier, right? So it's a simple contract, nothing special. However, we have a second contract which does the exact same thing, but instead of having an only owner modifier, we are simply having a private function, which again does the same thing, which simply checks that the owner address should not be a invalid address, a 0 address. Instead of modifier, we just replace it with a private function. And what we did was in function 1, 2, and 3, instead of modifier, we now have it as a private function. So it still does the same thing. It's still when you call the function 1, it will check the owner's state first and then move forward. So exact same behavior, I think exact same lines of code in both contracts. But when you come down and you look at the results, you see difference. And the difference is the contract that use modifier has 2,324 characters in the bytecode. And the contract that did not use modifiers and simply used private function, it had only 1,800 characters, which means that if you use simple private functions, you are actually saving your contract size. So your contract size is less. But if you're using modifiers, the contract size is more, right? That means if you ever run into a scenario where your contract size is getting bigger and bigger, and you want to reduce the size, and you know that, okay, now I cannot remove any more functions because that disturbs my intended flow, and you cannot remove any functions, you have already done all the optimizations, then as a last resort, you can do this. You can remove your modifiers in the contract and use private functions instead, right? And the result will simply be that if you use private functions, you are able to reduce the size of the contract. But why does this happen? I can ask this question to you in case anyone wants to answer. Why do you think using modifier is actually costing us more space than using simple private functions? In case anyone wants to try or guess on this one. Okay, cool. So the reason is actually pretty simple. And if you know how modifiers work, you will understand this. So let's say in this modifier, the only thing that happens when you are using a modifier is what you're doing is you're saying, hey, whenever I call this modifier in any function, whatever code is in the modifier, paste it in the function first, and then execute the rest of the function. That's what modifiers are, right? We are basically modifying the behavior of the function by adding an additional line on top of it. So let's say this function one had 3 lines of code initially, but now that it has only one modifier, it will first execute the modifiers line and then it will go down to its own 3 lines, right? So when you're using modifier and you're compiling the contract, what essentially ends up happening is every function that uses the modifier basically writes the code of the modifier in that function first while compilation, and then the rest of the function, right? So that basically means the size of the function just increased because it's containing an additional line of code of the modifier. However, in private function, that is not happening. In private function, we are not really doing that. Unless a function is called, we don't really care what's written in the specific function logic, in the private function logic, right? So because we are not concerned about that, we are able to shrink the size of the contract by a couple of characters, and we are able to get more functions maybe because we have now shortened the length of the contract, right? So that's another technique you can use. So if you read this article, you will understand that it's not just about gas, it's also about optimizing the space in the contract, because chances are if you write a lot of functions and you're shipping a lot of different versions, you might hit a scenario where you are not able to even deploy the contract, and you don't want that. You want to be able to deploy the contract, and for that you have to reduce the size of the contract to lower than 24.5 kilobytes. So keep that in mind. All right, so that, I think that's pretty much it in the bytecode section. And again, the reason I'm sharing the links in the chat box is because I want you to go through it. I want you to understand how exactly each of this works, and maybe drop questions in the Telegram as well. I'm there in the Central DAO Telegram. Uh, Now comes the stage 3, which is optimizing the gas in Solidity, which I think is an interesting topic. Quick question to both all of you here. What do you think saves more gas, mapping or an array? Which one is more efficient in terms of gas? And maybe you can explain why. And it's an open question for anyone. Can you guys hear me? Cool. Okay, so if there's no one, then I can proceed. Yeah, go ahead.
Yeah, sir. Having one, just guessing one. Hi.
Hey, yeah, I can hear you.
Yeah, sir. I just guessing something like in array we just want to use just allocating the memory
Mhm.
locations. While in mapping we just pointing to just we just mapping the two memory location at the same time.
Okay.
This is the answer, I guess so. I'm not pretty sure.
So do you think mapping is more efficient or array?
Yeah, mapping, sir.
Okay. So you think mapping is more efficient, right?
Yeah, I guess
Okay,
so.
got it. So your answer is right. Mapping is more efficient slightly, but the reasoning is off. So let me tell you why that's the case.
Okay, sir. Yeah,
Uh,
sure.
let's say you have an array. Yeah, anyone wants to answer?
Uh, Mapping is more efficient because consider mapping as a phone book where we can find easily the key, so we can find the value. But array, it is an iteration of we need it goes like an iteration of values. So I think it consumes more gas than mapping. In mapping, we can easily
Got it.
find the value using the key.
But you can also do an array, right? You don't really have to. So let's say you want to figure out what's there in index 2, you can just pass index 2 and you will get the value.
But it goes one by one, right?
I mean, not necessarily, right? So let's say you can have a function which says get array index at 0. So you just pass 0 and you get the value. You don't have to iterate over.
Okay.
Yeah, I mean your logic is right. So that's why we're doing it. We're not. I'm not delivering a lecture. It's just a brainstorming session, right? So well tried, nice try. Uh, Maybe I can explain the reason behind it. So both array and mapping are important, and you will use it whenever you want to, and based on the intended behavior that you have in the contract. But it's just a bit effective, in efficient in terms of gas to use mapping than array, because let's say we have this mapping and array, right? So that I've written here right now. Array 1, 2, 3, 4. So basically that means that from index 0 to 3 we have values. Now when we are, let's say we want to fetch a particular value of index 2, we will pass index 2, 0 and 2, and that's 3, so it will return 3, right? And let's say the same thing is in mapping as well, and when I pass index 2, and the same values are there as well, so it also returns, okay, for key, in mapping there is key and value, so for key 2 the value is 3. Both of them returns the value, both of them can be used, but the difference is that when we are using an array, Solidity compiler or the EVM adds an additional check of validating whether or not you are passing the right index in this array or not. Because if I pass 10, then it should panic and it should return error, correct? That's an additional check that the compiler adds on to this. And that is what makes array slightly more costlier than mapping. Because in mapping, if you pass 10, it won't panic. It will just return the default value, which is, if there is nothing, it will say 0, right? So there is no additional check in mapping to verify whether or not you're passing the right index, because there are no index in mapping, right? There is just a key and a value, and chances are the key is right, so you will get the value, or the key is wrong, and you will get the default value, or whatever it is. So if it's a uint to uint mapping, and there is nothing, so you will just get 0, right? But in array, if you are passing the right index, 2 or 3 or 1, you will get the value. But the moment you pass an absolutely wrong index, which is, let's say, 100, compiler will be like, hey man, this is not even valid. There is no index as 100, so I'm going to panic and I'm going to return error. Because of that check, it makes arrays a bit more costlier than mapping. Keep that in mind. By no way am I saying that always use a mapping and never use array. If you have to use array, you have to. But the point of discussing all of these things is that you can make an informed decision and not just blindly follow what you think you should do, right? And even before the thing that I mentioned here in modifiers and versus private function, it doesn't mean I'm encouraging you to always use private function and never use modifiers. Modifiers are great. They make your code readable. It's an interesting thing to use. What I'm saying is, if you hit a particular scenario where your contract is hitting the threshold of per bytecode size, then you need to consider, and then these tricks will come in handy. And not in a general contract. In a general contract, there's a lot of space for you to do a lot of things. So keep that in mind. All of these are suggestions and tricks. They are not strong recommendations of how you should build contract. Anyways, getting back, tricks to optimize gas. First, we understood that mapping versus array. Mapping can be slightly more efficient. Second one is arrangement of if-else conditions, or sometimes we also call it as this trick as short circuit evaluation. Anyone who has heard about this before, because this is not really specific to smart contract, it's a general programming term. So anyone who knows what this is about? Short circuit evaluation. Anyone? Deepak, Gulshan, or
Actually, I haven't heard about short circuit evaluation.
Cool, no worries. So this is basically a trick that you can use to optimize gas in a condition where there are multiple if-else statements in a function, right? So again, let's go and understand with example, because that's the better way. So
maybe in case of or condition, let's say there are two
yes,
conditions. First or is evaluated as true, so compiler will not evaluate the second condition in the if, so it's considered as a
exactly,
false. This is one of the examples.
exactly. Perfect. Yeah, that's actually great. So let me explain. And it's the same thing that Gulshan mentioned, right? So this is a way for us to optimize gas with a simple trick, which is external view returns whatever, it doesn't matter, and then we come into the function body. There is a first if condition, let's say, and there is a condition here, and there's a second condition, and the third, and so on, and the last one. So this design basically means that you already have a lot of if-else conditions, which I don't like personally. So if you like, the first course of action is, if you can, get rid of nested statements. Keep your contract as simple as possible. But if you cannot do that, and if you still have to use this nested structure for whatever reason you're building, try to keep the first condition as the one which is the most highly possible value that might occur when someone calls this function. So let's say there are a couple of conditions, but the likelihood of condition 1 to come true is more. So whenever someone calls this function, chances are they will, you think that they might fall in this if bracket more. So what you should do is put that on the very top, right? And the moment you do it, is what you're doing is you're saying, hey, once this condition is true and it's hit, just execute it and stop the execution. Stop the execution means now you're no more using gas. Otherwise, let's say you think that condition 1 is the one that is supposed to be occurring very frequently, but you put this condition at the very last, for example, right? You put it here, for example. Now the problem that is happening is there is a jump opcode in Solidity. So what that does is, if this condition doesn't match, it jumps to the next condition. If this doesn't match, it jumps to the next condition. And if this doesn't match, it jumps again to the next condition, and then it evaluates. So if you have put a condition which is highly likely to occur every time at the very end, then you are making a lot of jumps in that function, which means you are taking a lot of gas in that function. So this trick basically means that if you have a nested structure, put the condition at the very top, the one that you think is highly likely to occur, and based on that occurrence, you put the rest of the conditions as it is. By that, what you're doing is, whenever, like the moment this condition occurs and it's true, the EVM executes it and then returns the function, and you are able to save gas. Otherwise, you keep jumping from condition to condition, and that might cost a lot of gas. Did someone raise hand? No, but I guess, yeah, fine. Cool. So does that make sense, Deepak, Gulshan?
Yes.
Perfect. So that's an additional trick that you can use. And these are tricks that you often forget, but it's really interesting to keep this in mind because you're actually able to save gas using this. Okay. Third trick is to optimize storage reads in a contract. What I mean by that is, in a function, whenever you read a particular storage, you end up using more gas, right? And again, let's go to example to understand this. Central DAO snippets, and we go to storage read. Hopefully this, or maybe I can go to the loops. This is a better example. So look at this contract. It's a pretty simple contract, and we are using loop as example here. What we are doing is, there's a threshold state variable, which is the state, and there is a mapping of data. There are two different functions. One of them is a costly function, and the other is a cheap function, right? The operation that we are doing in both the functions is pretty similar. We are taking an array of values, and we are passing all of those values through a loop, and we are checking that only if the values are lesser than the threshold, which is 100, we update the mapping, else we don't, right? And it's the same thing is happening to both of these functions. Now, maybe I can just deploy this contract and show you live what the let's try to deploy it. I am deploying it on BSC testnet. All right, are you able to see the screen properly? Should I zoom in more? Okay. So I have a dummy array here that I'll pass in both, right? And we will use this console to see what each transaction cost. So we have this huge length of array that we are passing in both the functions. We'll first call the costly function. And all the values are less than 100, so it should pass, hopefully. So we just executed the first one. And there's a particular gas that was cost. And let's say there's a second one. Okay. All right. We did both the functions, and the gas that was costed was this. So in the costly function, we had to use this amount of gas, which is 391K plus, and in the cheap one, we only used 71K, right? Again, there could be other reasons behind this difference on gas as well. One of them being that we called the costly function first and the cheap one later. So the data that was updated was already there. But again, don't worry about that. The important part that you need to understand is this. In this for loop, in the costly function, what's happening is every time we check that the incoming values should be less than the threshold, we are actually calling the threshold. Threshold is this state, right? And it's a storage, it's an actual state variable. Whenever you call a state variable, you have to pay some sort of gas because you're calling directly from the state, right? Uh, I hope you know what storage, memory, and call data means in Solidity. Every state variable is stored in a storage location, which is costlier. The memory location is slightly cheaper, and call data is for function parameters, right? So basically, storage is costly, memory access is cheap. Now, what we are doing in costly function is in the if statement, for every new value that we have, we are checking it whether or not it's less than the threshold, but we are actually calling the storage read directly from the threshold, right? So essentially, the longer you run this loop, let's say you are passing array of 50 elements, you will run this loop for 50 elements, and you will read this state variable for 50 times, right? Compared to this cheap function, which does the exact same thing, but it with one slight difference, which is it caches it out. So it includes a local variable within the function, which is threshold local, and it reads the threshold state variable just once, which is on line 20, right? And the rest of the time in the loop, it only uses its local variable. So the way the local variables are stored is in memory, but this state variable is stored in storage, right? And like I said, storage is more costly than memory. So the cheap function is smartly reading from memory, not from the storage. And because it's reading from the memory, it's actually costing less gas than the costly function because it is reading directly from storage, right? And it's with these simple tricks in Solidity that you're able to save such huge differences of gas, right? So keep these tricks in mind because the simple trick is reduce the number of storage reads in a function. The more you read directly from storage, the more you are costing gas for your users who will not like you for this. And you need to protect the money of your users. So try to read from memory more and try to reduce the number of storage reads in your functions. And I hope that was clear. And yeah, this is what we just explored in loops. And then maybe we can come to the security part of the smart contracts. Any questions so far in gas? Anyone? Okay, so let's move to the storage, stage 4, which is the final stage of the contract. And I think I'm slightly over time, so I'll try to wrap it up quickly. Um, Part of being a good smart contract developer is to be able to write secure contract as well. And technically, whatever I just mentioned right now, which is bytecode optimization, gas optimization, all of those comes later. The first is security. Uh, if your contract gets hacked, it doesn't matter how optimized it was. So understanding the limitations of your contract is very important. So at a very brief glance, it looks like smart contract is a big deal. You are writing immutable code. It's decentralized. It's transparent, so it's very secure. But when you actually look into the data, there has been a lot of hacks, right? Since 2020, since the year I joined in Web3 security, the hacks keep happening. Every now and then there is a report that millions of dollars were lost for some smart contract hack. So you know that something is not right, and there are multiple reasons for that. Uh, First is smart contracts are immutable. So once you write a code, it's very hard to change. And if there is a bug, chances are it will get exploited. Secondly, smart contracts also depend on the chain that they're deployed to. So if that chain goes through some major change or some major security flaw, your contracts might be affected as well. Uh, the next point is whatever we're doing right now in Solidity or with blockchains, we are still at a very early stage and we are getting close to perfection, but we are still in nascent stages. So with every Solidity version that comes up, for example, you might see that the previous version had some flaws, which this version might not have. Uh, and that will keep on happening unless until we reach to a stage where it's actually very good. The versions become very secure, right? So all of these reasons combined, and there are more reasons. So for example, lack of proper testing, lack of auditing, lack of a good security review in contracts, all of these essentially lead to hacks, right? And there are two possible solutions for this. First is following best practices when developing Solidity, some of those that we already explored, and most importantly, writing test cases or writing first test cases yourself properly for every specific function that you have in the contract, and making sure that you're covering all the functions, right? So good coverage means you have tested the contract thoroughly. And secondly, going through audits, or if you are an auditor, then auditing contracts very well is part of your very big responsibility. Uh, so I'll talk about both of those things, but first I'll talk about the development part because I think most of you are developers here. So there are a couple of important tricks to keep in mind when you're writing Solidity code and you want to write secure Solidity code. The first one is I know you might have heard about it. It's a reentrancy issue. So whenever you're doing an external call, be very careful of where that call leads you to. If it's leading you to a smart contract, which basically means for a particular period of time, the third party contract will have access to that call and they can do whatever they want with that. So it's your responsibility to make sure that you're using all the important techniques properly while interacting with external call. And the first one is to use check effects interaction pattern. Again, a term that I would like you guys to read more about. And this is a good example for that. So check effects interaction pattern means very simply that if there's any function that is doing external call, for example, this one, right? So it's basically sending the ether to a different particular message or sender, which is basically transferring an external call, right? Uh, in any function, or let's say it's not about just sending ether, it's about interacting with other contract or making a delegate call or a call to other contract, any sort of external call. In that, there is a pattern that you should follow, which is first you do the check, then you have the effects, and then you have the interaction, which means anything that you have to check and validate should come first. Then any effects that that this function is supposed to have comes after that. So any state updates needs to come after that, right? And the external call, which is the interaction part, comes at the last. And the reason this is being highlighted as CEI pattern is because if you know the famous DAO hack, again, I'm going to write here, DAO hack, re-entrancy attack. So if you have read about it somewhere, you know that in that hack, the core reason behind that hack was external call was done before updating the states. So the hacker was able to re-enter the contract again and again because the states were not updated, right? And that's a very brief definition because I have short time, but you still need to go and explore that. And if you just if that contract had a simple fix, which is uh, interacting or external call was placed at the very last and state updations were done before that, that entire attack would have been prevented. It's just a one line flaw that lead to $1 million loss, right? So protecting yourself from reentrancy attack is very important, right? So first is check if it's interaction pattern. Make sure you follow that whenever you have a function that does external call. Second is non-reentrant modifier of OpenZeppelin. So OpenZeppelin has a contract called a library called reentrancy guard, and again something you should check into. So and this has a modifier which is called non-reentrant. So whenever you're writing a function that you know is going to have external call, the first order of business is you should just import this contract and you should include that modifier to that function, because that will be acting as a checkpoint which ensures that your function cannot be re-entered by any hacker. So that's a second trick for that. Third point is input validations. So anytime you have a function which is public or external, first of all, try to keep your functions very restricted. So you can mark it as private as much as you want. But again, it's not practical. So you might have functions that is publicly accessible. And for all those public accessible functions, you need to have input validations. You need to validate every parameter that is being passed in that function. Unless you do that, chances are someone can pass a wrong value or an invalid value that might even cause a lot of different effects, right? So for example, if you have functions withdraw and you're allowing people to pass amount that they want to withdraw, right? But and let's say this is the one. So let's say you are just allowing them to pass whatever you want to withdraw, just withdraw from here, and amount message.sender, whoever is calling will get the amount, right? The problem with this function is we are relying on the user. So we are saying, hey, whatever value the user is passing here, just let them get that amount, right? We are not even validating that whether or not this user is supposed to get that amount or not. So the way to fix it is having input validation check, which actually checks that this amount should actually be greater than the balance of the user that is there in the contract. Now with this one line, we have imposed a rule, a law that says that you can only withdraw the amount that you actually have in this contract, not more than that and not less than that. You can choose to withdraw all of it if you want, but you cannot exceed the balance that you already have. So you only withdraw the amount that you deserve to withdraw, right? But if you don't validate this, it's really hard for you to get a right action that you might want for this contract. Fourth point is checking access controls. So which basically means that in every contract there are some roles that are specific for admins of the contract, and I don't like the word owner. I prefer using admin. So there could be functions that allow only admin to update a particular state or only admin to update a particular value. But if you don't attach that only admin modifier, which means that only the admin can access this function, then that basically means that anyone can access that function. And if admin functions can be accessed by anyone, then that's a major threat to your contract. So make sure you're not doing that. And the second stage for this is the smart contract audits. So in case anyone wants to go to audits, there is a 5-step process that I follow, which is understanding what the code base is about and documentation that the client gives you. Second is evaluation of test cases, which basically means that test cases will help you understand what the contract is behaving like. Then there are actually very, very cool tools that I would like to share with you, which is, and some of them that I use, which is Slytherin. So these are tools you can actually use in your own contracts whenever you want. Let me show you a quick example. So So for instance, there is this contract that I have, which is this. So this is a contract that I have. It's called dummy contract. And I basically want to run an automated test. An automated test is basically you asking the computer, hey, computer, tell me what's wrong with my contract. And it will give you a list of different issues that it might find based on historical occurrence of those issues that might have occurred in the smart contract hacks. And if you simply run this command, which is slithering. So what this gives you is a long list of issues that it found in your contract. Now, the problem with automated test is that it could give you some false positives, like it could view some of those things as issues, but they are not really issues. So you need to still be able to filter those issues, but it does give you a lot of different issues that it found in your contract or the libraries that you're using. For example, it gave me a potential reentrancy attack, and I need to check this out because it's highlighted in red, and I need to figure out if it's actually true. If it is true, then it's a very big help because I was able to find this issue with just one command, right? And there are different flags that you can use with this. So I hope it was called print even summary. And